Have you ever just stared at the periodic table and felt completely overwhelmed? I mean, it looks like this crazy, intimidating chart of random letters and numbers, right? But what if I told you that it's actually the ultimate decoder ring for how the entire universe behaves? What if you essentially had a cheat sheet that could literally predict the future of a chemical reaction? Well, welcome to this explainer. I'm absolutely thrilled to be your guide today as we take this seemingly complex grid and transform it into a beautifully organized map. We're going to decode the periodic table together, and trust me, by the end of this, you are going to see the chemical world in a completely new light. So let's just dive right in.
Here's our roadmap for today. We're going to start off by decoding the periodic table, then explore the power of valency, look at metals versus nonmetals, and zoom in on the electron blueprint. Finally, we'll wrap it all up with predicting chemical trends.
All right, Section 1, Decoding the Periodic Table. Let's learn how to read this universal map. What's truly wild here is just how brilliantly organized this grid actually is. You've got over 100 isolated, identified chemical elements laid out here. And if you look closely, they're arranged in order of increasing atomic number from left to right. That just means each element has exactly one more proton than the guy right before it. But the real magic? That happens in the rows and columns. The horizontal rows, those are called periods, numbered 1 through 7, and they actually tell us how many electron shells an atom has. Then you have the vertical columns, called groups. Elements hanging out in the same group share the exact same number of outer electrons, which practically forces them to have very similar chemical properties. So an element's placement isn't random at all. It's basically a physical address. Now, when you zoom in on any single element's box, you're going to see two numbers, and man, it is so easy to get them mixed up. Knowing which is absolutely crucial. So here's a little insider trick straight from examiners. Just remember, mass equals massive. The mass number is always the massive number, the larger of the two, which means the atomic number has to be the smaller one. Just keep that little nugget in your back pocket. It'll save you a ton of confusion later. Moving on to Section 2, the power of valency. Let's talk about the combining power of atoms. Valency is basically an element's combining power. It tells you exactly how many bonds a specific atom can make with another atom to form a compound. And it does this by either losing, gaining, or sharing its electrons. Take carbon, for example. Carbon sits right there in group IV, which means it has a valency of 4. So, a single carbon atom can share its 4 outer electrons to make 4 single bonds, or even 2 double bonds. It is perfectly equipped to just reach out and connect. And there's this incredible symmetry that perfectly maps out the pattern of valency. Your group number directly dictates your combining power, but it follows this beautifully symmetrical hill. Over in group I, the valency is 1. Group 2 is 2, group 3 is 3, and it peaks right at group 4 with a valency of 4. But then watch what happens. It descends. Group 5 drops back down to 3, group 6 is 2, group 7 is 1, and finally, group 8, the noble gases, have a valency of 0. They've got full shells, so they don't need to bond with anybody. Now, this group number doesn't just tell us about sharing. It actually tells us what kind of electrical charge an ion will have when it reacts. Metals, which hang out on the left side of the table, desperately want to lose electrons to get that full outer shell. So a metal in group I loses its 1 outer electron, leaving it with a 1+ charge. Nonmetals over on the right, they're a bit greedy. They want to gain electrons. A nonmetal in group 7, like chlorine, just needs 1 more electron to fill its shell, so it snatches 1 up and gets a 1- charge. It is quite literally an elegant system of supply and demand. Up next, Section 3, Metals versus Nonmetals. Time to look at the Great Divide. There is a literal line drawn in the sand here, or, well, a zigzag line drawn across the table. The metallic character of elements steadily decreases as you move from left to right. All those elements packed on the left, those are your metals. They readily lose electrons. Way over on the right side are the nonmetals, which prefer to accept electrons. But look at that step-like structure right there in the middle. Those are the metalloids, or semimetals. They sit right on the fence and actually display properties of both metals and nonmetals, which is pretty cool. So the crucial point is understanding how these two sides of the track differ in the real world. Metals, as we generally know, are malleable. They can be bent and shaped, they're fantastic conductors of electricity, they have high melting and boiling points, and they form basic oxides. Nonmetals, on the other hand, are completely different beasts. Physically, they tend to be flaky and brittle, with super low melting and boiling points. They're really poor conductors of electricity, and they form acidic oxides.
It's a stark contrast, and it's all entirely dictated by whether they want to give away or steal those outer electrons.
All right, Section 4, the electron blueprint. Let's zoom in on the atoms themselves. This internal structure dictates exactly where an element gets to sit on our map. Take a look at the blueprint for chlorine. The electronic configuration is just how the electrons are arranged into shells. For chlorine, it's written out as 2, 8, 7. Now, I know it looks like just a random string of numbers, but it directly corresponds to the actual rings around the nucleus. You've got 2 in the inner shell, 8 in the middle, and 7 on the outermost shell. Let's decode that 287 just a bit further, because honestly, this is where the magic happens. Those numbers are literal coordinates. Because there are 3 numbers in that sequence, it means chlorine has 3 occupied electron shells. That instantly tells us it lives in period 3 of the periodic table. The very last number is a 7, meaning there are 7 outer electrons. Boom, that places it squarely in group 7. And remember, when atoms collide, it's those outermost electrons that do the interacting. Elements with the same number of outer electrons behave in remarkably similar ways. You don't actually have to memorize a bunch of random properties if you can just read the blueprint. Moving to our final part, Section 5, predicting chemical trends. It's time to start foreseeing reactions.
So if there is one crucial point to take away from everything we've talked about today, it's that the periodic table is not just some static storage cabinet for boring facts. It is a dynamic, predictive engine. Because of these incredibly structured patterns of electron shells and groups, we can literally predict an element's boiling point, its melting point, density, and reactivity without ever having to test it in a lab. If you know the behavior of one element in a group, you can accurately guess the behavior of the element sitting right below or above it.
Let's actually test that predictive engine with a pretty famous example using the group I metals. If you drop lithium in water, it fizzes and reacts quickly. Go down one step to sodium, and the reaction is way stronger. Down another step to potassium, and it literally bursts into flames. By observing this pattern, we don't even need to physically test rubidium or cesium to know that their reactivity will increase explosively as we go down the group. And by the time we reach the bottom element, francium, well, it's incredibly rare and highly radioactive, but based on our cheat sheet, we know for a fact it would react more vigorously than any of the others. We just predicted its extreme chemical behavior simply by looking at its zip code on the table. We've gone from staring at a confusing grid of letters to reading the very blueprint of chemical reality. You now know exactly how to find an element's combining power, predict its electrical charge, map the divide between metals and nonmetals, and even foresee explosive reactions before they ever happen. But honestly, this is really just the beginning. Now that you hold the ultimate decoder ring, what other secrets of the universe might this cheat sheet reveal to you? Keep exploring, keep questioning, and keep using the structure around you to decode the world. Thanks for joining me on this explainer, and I'll catch you next time.